the beginning of 6.3, we're taking a look at graphing exponential functions. So what I have here is a table that you would have to fill out if you were trying to graph a exponential function, 2 raised to the power of x. Remember that if you are going to plug in a negative number for x, that would mean that you would have to move that 2 and the negative exponent to the other side of the fraction bar, and then you can write that as a positive one. So I have 1/2 here. If I plug in 0, that would be 1. If I plug in 1, that would be 2. If I plugged in 2, that would be 4. And then if I plugged in 3, that would be 8. And if I plugged in 4, and you know that every time this doubles over and over, I could write all of these on here to drive home the point, but I think that a few of them is probably enough. So basically, if I were to graph this at 0, here we are at 1. At 1, we're at 2. And at 2, we're at 4. And then 8. And you can see that it gets very big very quickly. And if you go to the left of the y-axis, then you're going to see that the points are getting closer and closer and closer to 0 without actually ever touching 0. And you're going to do your best to sketch. And that's an awful sketch. Let's try this again. Doing my best to sketch what's going on there. Which actually, this is a little bit better, but the end of it I don't really like very much because it's not going away. There we go. Okay, that is me sketching a rough graph of f of x equals 2 raised to the power of x. Beautiful, right? What happens if somebody asks you to use this table to graph the inverse of f of x equals 2 to the x? So remember that the inverse of this is going to be this. Okay, you can go through all of the steps to figure that out, or you can recall that that's what it looks like. And I want you to know that because we've looked at the past about characteristics of functions and their inverses, one of the things we noticed is when you have a function, its inverse actually has the same domain and range. It's just flip-flopped. So the range of my original function is going to be the domain of my inverse, and the domain of my original function is going to be the range of my inverse. So you can almost take all of these numbers here and put them in this column, and same thing with the other way. So I could have 1/2, 1, 2, 4, 8, and so on and so forth. And then on the other side of this, I would have -1, 0, 1, 2, 3, and so on and so forth. So I'm going to go ahead and graph these ordered pairs. Okay, so the first ordered pair is 1/4, 2. So I'm going over 1/4 and down 2. Actually going to make that like right here. 1 over 1/2 down 1. Then we have 1 over 0. Then we have 2 over 1, 4 over 2, 8 over 3. So you can kind of see that this is going to take on this look. Much more difficult and challenging to draw that. But yes, I actually had to erase and redo that a couple of times because I had bad handwriting here and I was confusing myself. Bad handwriting is bad. Okay, let's go to the next page. Okay, so here is a picture of what I just graphed, but you can see that in blue is the original function, and then in red is its inverse. And again, like we talked about before, they are a reflection of each other over the line y equals x, which is that perfectly diagonal line that goes through the origin. Notice that the characteristics of an exponential graph, this is a graph that is increasing, that the multiplier is a number larger than 1. That there is no x-intercept, so this never touches the x-axis. The y-intercept here is 0, 1 for this particular example. The x-axis is a horizontal asymptote. That means that this is leveling off here at the x-axis, and that the graph is increasing slowly and then rapidly. So those are just 4 things to notice. And then I want you to notice some things about its inverse, the logarithmic graph. There's a lot of opposites here. For instance, the exponential graph had no x-intercept. Well, the log has no y-intercept. The y-intercept is 0, 1. The x-intercept is 1, 0. The x-axis is a horizontal asymptote. For the log one, the y-axis is a vertical asymptote. And then this says the graph increases slowly, then rapidly. Well, for the other one, the graph increases rapidly and then slowly. A lot of opposites. It's not always like that. Every now and then you'll have something that doesn't do what you think it's going to do, but for the most part, it's really interesting, all of the parallel features that we have for the original function and its inverse. Here's another one asking us to sketch the graph of f of x equals log of 0.5x and log base 0.5x. And they even gave us all the information here. I'll tell you right now, I would be dealing mostly with things that I can kind of imagine where they go. So I'm going to start with going over 4 units and down 2, going over 1 unit and down 0, going over 1/4 of a unit up 2, and then going over 0.0625, going up 4. Notice that when you graph this, it is got a vertical asymptote, and there, oh gosh, I'm so bad at this by hand. Let's try that again. Oh, there we go. Okay, that's what we've got. That's our original. This is log base half of x. Find the inverse of log base 0.5 of x. Well, because I know about inverses with logs and exponentials are inverses of each other, then I would know the inverse of this is actually 0.5 raised to the power of x. What if you didn't know that? How would you find it? You can go through the process where you first rewrite everything with a y instead of function notation. Then you would switch the y and the x, and then you would want to recancel or isolate the y. And the only way you can really do that is if you switch this to an exponential function, which means the 0.5 becomes big, and the x and the y switch spots, and log goes away. And so you can kind of see the inverse. That's where it came from. They want us to find the inverse, and that's what we did. You look at the next page. The next page is going to ask us to create a table and graph the inverse. Now, we have a table right here, and we know lots of things about graphs and their inverses. So I'm going to actually take a picture of this table, and I'm going to save it. Let's go ahead and, I don't want to have to keep flipping back and forth. Done. Save. Okay. Ooh, it didn't like. And then let's go to the next page. I'm going to add this existing image. I've got it here. Let's put it in here. Okay. So this is the one from the other page. I'm just going to stick this right here for now. Create a table of values and graph the inverse of. Oh, hold on a minute. The inverse of, it's the inverse, which is 0.5 raised to the power of x. There it is. And I can go ahead and I can plug in numbers, or I can remember that the inverse function's range is going to be the domain of the original function, and so on and so forth. So this is how I'm going to do it. All this -10, all this stuff now goes in the x. I'm doing that. -4, -2, 0, 2, 4. And then, so I'm just going to say this is now my x, and this is going to be my inverse of x, which is 1024, 256, 64, 16, 4, 1, 0.25, 0.0625. And now I'm going to start graphing these, right? So I'm going to use the same ones that I used from before. I'm going 4 units over, 2, 3, 4, down very little, 0.625. I'm going 2 actually I'm not going down, I'm going up. I need to 4 over up, right there it is. 2 over up a quarter, 0 over up 1, -2 is up 4. And so if I were to draw this, it would look something like this, where it is slowly approaching 0, and that's what that would look like. Of course, notice that the base for both of these was a number between 0 and 1, which means that we want you to notice, I've got to move this, there we go. The base, there's my graph. The base is a number between 0 and 1, so this graph also has some interesting characteristics. Notice, again, this was our original, this was our original, and then this was our inverse. Even though they overlap, they still are a reflection of each other over the line y equals x. Notice that the exponential graph has no x-intercept. That's the blue one. The y-intercept of it is 0, 1. The x-axis is a horizontal asymptote. It's approaching the x-axis. And the graph decreases rapidly and then slowly. And then if we look at the log graph, it has no y-intercept. The x-intercept is 1, 0. The y-axis is a vertical asymptote. The only thing here that's kind of funny is our last characteristic matches. The graph decreases rapidly and then slowly. The graph that's one thing that they share. So that's a thing. So really interesting points that you can notice from graphs and their inverses. The characteristics are just really interesting. Let's go to the next page. Okay, so we have some questions that you might run into here and there. The typical questions asking you to interpret a graph. For instance, they want you to estimate the g of 40. Remember that this is an ordered pair where 40 is the x and we're looking for the y. Here is where 40 is the x. That would mean y is -3. B is asking us, what value of x will give me a y value of -2? Well, y is -2 right here. So if I file this over and up, then x must have been 10. So I would say x equals 10. When x equals 10, y equals -2. The domain, how far left or how far right? We would say that this goes from 0 to infinity. Never actually touches 0. What is the range? We're going to say from -infinity to +infinity. Then they ask, is the base of the function greater or less than 1? So I guess basically you're asking yourself if this function is increasing or decreasing. And in this case, it's decreasing. So we're going to say that the base is less than 1. Let's try the next one. This one I want you to pause and do this on your own and then come back and compare your answers with me. So go ahead and pause right now. Okay, so the first question says estimate g of 150. So if 150 is the x value, the y value would be somewhere, looks like 4.5-ish. Then it says estimate what value of x will give a g of x of 5. That means 5 is the y value. So I would follow 5 over to the line and down. Looks like 250, where x is 250. The domain of this is from 0 to infinity. The range is from negative to +infinity. And this is increasing, so we're going to say that the base is greater than 1. So that will be the end of this video.